Okay, so now let's proceed to see logistic regression. You know, the limitation of chi-square test is, we have said that for 2 by 2 contingency table, we can use the odds ratio and relative risk. And then if the dependent or the predictor variable have more than 2 categories, then we go for using chi-square test. But in the case of chi-square test, what we can do is we can only test a single predictor categorical variable with a single outcome variable at a time. It cannot control the effect of other confounding factors. So in such a case, what we are going to do, if we do have a plan to include multiple predictor or risk factors associated with a single categorical outcome variable having a binary category, then we are going to use the logistic regression. That is the reason why we go for logistic regression rather than using the chi-square test and other 2 by 2 measures of association, including the odds ratio and the relative risk, So now we are on the way of just diving into the details or advancements of statistical modeling. So now, generally, before directly saying about logistic regression, what does a regression mean? What does a regression mean? Okay. A regression analysis is a tool to explain the impact of changes in one or more of the independent variables on the dependent variable. What will be the change in the outcome variable given the change in the certain amount of a predictor variable? That means, for example, what will be the change in the systolic blood pressure of a patient with a change in the salt content of a food that the patient is using? So the amount of the salt, if it increases within the food that the patient is eating, then the systolic blood pressure of the patient is expected to rise, So regression is just to mean that prediction of the change in the outcome variable. That means we are saying outcome variable is the disease or any medical variables that we are going to measure, given the change in the predictor variable or the risk variable. So regression is prediction of the change in the outcome variable given a certain amount of change in the predictor variable. That is generally regression. And actually, if I were in front of you physically, I would have just have a chance to tell you about the historical background, how the name regression has been given, Okay. Maybe just let me pause the video record over here and let me tell you. Okay, so regression analysis investigates or exploits the relationship between two or more than two predictor variables. The relationship between two or more variables, then we can get information about one of them through knowing the values of the other. By knowing the values of the predictor variable, we can know the change in the outcome variable. Like, for example, in the clinical setup, there are different dosage levels for different drugs and vaccines. Yeah? You see, the dosage of each drug or vaccine has been determined by such approach. By how much value of the change in the drug dosage size, the disease will change, So 500 milligram or 250 milligram, whatever, in the form of tab or in the form of IV or intramuscular injection, whatever. The dosage of the drug is the predictor of the disease status, the change in the disease, So knowing the dosage level of a drug or knowing the dosage level of a vaccine will enable us by how much the change in the disease status will occur. That is regression, the purpose or the objective of doing regression, That is really very fundamental. So regression can be used for prediction. Like, for example, the survival status of a patient by taking a certain type of drug. For how much? For how many times of months or years could the patient survive? That is a way of prediction. by taking a certain drug with a certain amount of dosage for a certain duration, then the prognosis of that disease status will be predicted, The estimation, that means the amount of level of a certain variable, whether it is mean or proportion, based on the sample for that of the total population. And testing the hypothesis, and then finally modeling the relationship. At least just to know or to have a clue of causation, to have a clue of causation. Therefore, mathematically, we will just, as you know, in your basic biostatistics course, we do have the outcome variable y is equal to, that could be, the outcome variable is the change in the disease status or just the level of a certain variable, is equal to the predictor variables, the independent variables, x1 plus x2 plus x3. Therefore, the change in this either of the predictor variables will bring a change in the outcome variable. So this outcome variable y, as you know, is known as dependent variable, outcome variable, response variable. Like interchangeably, we use these terms, like birth weight ሊሆን ይችላል. Okay, the predictor variables are said to be independent variables, predictor variables, explanatory variables, and covariates. Other term is here again, covariates. Covariates. So interchangeably, we use these terms, Like the predictors for the birth weight could be the gestation of the mother, the age of the mother, the maternal characteristics like smoking, nutrition, whatever. A number of factors could be considered to just predict the change in the birth weight of the children. Okay, so in simple linear regression, we already have one dependent variable with a single independent variable. The independent variables are labeled as x and the outcome variable is y. So the outcome variable is always continuous in linear regression. So the relationship between x and y is described by a linear function. So changes in the y or in the outcome variable are assumed to be caused by change in the predictor variable. So the change in the outcome variable y is because of the change in the predictor or the x variable, that is the independent variable. So here is the general formula for estimation of the total value in the total population. The previous formula is for the sample, and this is for the population mean estimation, or the population outcome variable estimation method. The gamma is equal to beta naught, that is the intercept, plus beta 1 x1. This beta 1 is the effect of this predictor variable x, the amount of the influence or the effect of this x1 on y is expressed as the beta coefficient, plus finally the error term e, the unexplained variation of the outcome variable because of the missing predictor variables. Since as a human being we cannot explore everything and we cannot know every cause or risk factor for a certain disease. So unknown and missed predictor variables will be there. So because of this missed unknown predictor variables, there will be unexplained amount of variation of the outcome variable, and that is termed as the error term E. So this y is the dependent variable, x is the independent variable, beta naught is the intercept, and beta 1 is the slope of the line. That means the effect of the predictor variable x on y is labeled as beta 1. The slope is, just more of mathematical language, but to make it clear for you, the effect of a predictor variable x on the outcome variable is labeled as beta 1. That is said to be the slope. And this E is the error term that I have said previously, So in any regression, we are just trying to predict, you see, the amount of variation of a certain outcome variable, that is a disease, in a group of individuals, in a group of patients. Because since there is individual to individual variation, because of different risk factors, there will be a variation in the disease status of the patients. So that disease status variation among the patients is said to be the variation or the variance. So we are trying to predict the amount of variation in the outcome variable, that is the disease, among a group of patients or population with consideration of different risk factors or predictors. That is the idea of regression generally. You see, I'm just exerting more effort here because I wanted to just to understand what does this mathematical applications mean in the medical profession, you know. It is not only mathematics. So our estimated regression equation will be based on the sample data. The data that will be collected from the sample, it will be based upon that, and then the fitted or the predicted outcome variable y hat is equal to the intercept beta naught, that is, this is a sample, plus beta 1 x1 with a single predictor variable that is said to be simple linear regression. Like for example, if the outcome variable is systolic blood pressure is equal to beta naught, that is the intercept, without considering any predictor variable or without considering any risk factor, what will be the systolic blood pressure of an individual? Plus beta 1 age means the effect of this age with a 1 year increase. That means if the age of an individual increases by 1 year, what will be the effect of this increase in age, that is beta 1, on the systolic blood pressure? That is a mathematical formula or equation. For the total population, the systolic blood pressure will be the capital beta naught, this is actually B for the sample, plus beta 1 age, because we are estimating the change in the systolic blood pressure for the total population based on the result obtained from this sample, you know. That is the idea of doing regression analysis. So fitting the model is by using the simple linear regression model, that is beta naught plus beta 1 x1 plus the error term always. Always there will be error term, you know, because everything cannot be explained, as I have said before. So how do we develop this mathematical formula, and how do we know the line that which best fits our data? And actually this is a revision of your simple linear regression and multiple linear regression that you know in basic biostatistics maybe. So it has been said the method of least square, you know, the difference between the given score y, the observed or the real or the actual score y outcome variable, and the predicted score y hat is known as the error of estimation. You know, in the reality there is the actual score of the outcome variable y, and in our data, by using our data from the samples that have been collected, we are trying to predict that actual outcome variable y, that is denoted as y hat. So always there will be a variation of our predicted value with that of the real score of the outcome variable. Because as a human being, we cannot be 100% perfect. But we are just, it is expected to be our prediction to be more closer to the real score of outcome variable. So, the difference between the real score in the outcome variable with that of the predicted score that we have predicted with the data set is said to be the error of estimation. For example, if the real value of blood pressure for an individual is 181 by maybe 79, sorry, 181 is too much. If the blood pressure of an individual is, say, for example, 131 by 79, that is the real, let's say that's the real value of blood pressure. But a physician or any health professional trying to measure that blood pressure could measure as 125 by 65. You see? So the predicted and the actual values are not exactly the same. So always prediction cannot be exactly the same as with that of the real value. So the difference between the two is said to be the error of estimation. Okay, now if you see the distance or the difference between the estimated value and the actual value is smaller, then our prediction is better. If the difference between the real value and the predicted value is larger, that means we are far away from the actual value, you know. So the estimation is poor. So we expect our error of estimation to be smaller. When the error of estimation or the difference between the actual value with the predicted value is smaller, so that the predicted and the actual values are close to each other. near to each other. That means. So we are expecting to be have a better closer of the predicted and the actual value, you know. So the regression line or the line which best fits the given pairs of scores of the outcome variables, that means the predicted and the actual value, is the line for which the sum of the squares of this error of estimation is minimized. Finally, the distance or the variance or the error of estimation, that means the difference between the estimated or the predicted value and the actual value, is squared and it is summed up. So the minimum, the sum of the square of these differences is the better the prediction. So that is the line which best fits our data. So that is all of the curves or the lines. The curve with the minimum sum of squares of this error is the least square regression matrix that has been said, which best fits the data. So the least regression line for the set of observations x1, y1, x2, y2, x3, y3 up to xn, yn has the form y hat, the predicted value, is equal to the intercept a plus beta xi. That is a simple linear regression. Okay, so here it is, you know, there are pairs of scores, the predicted with that of the actual value. So these dots indicate pairs of this predicted and actual value of the outcome variable. So we are trying to draw a line which could have more dots on the line. So if all the dots are on the line, that will be the perfect prediction. But all the dots cannot be on the line, you know. But at least much of the dots are expected to be near to or on the line. Look over here, for example, this line. Only around 1, 2, 3. Only 3 dots are near to or on this line. And see this line again, maybe 1, 2, 3, 4, 5, 6, 7 dots. So in such a way, you can count the number of dots which are closer or on the line. And the best line which best fits this data is, you know, the line with this blue color. Because almost all dots are near to this line and onto this line. 1, 2, 3, 4, and those who are near to this line. And coming to here around again, near to this line, 1, 2, 3, 4. So the best line which best fits the data is the line in which the dots are near to that line and the dots on that line. Because if the paired data, that means the predicted and the actual outcome variables, are near to each other and near to the line, that is the line which best fits the data, because that line will have a minimum sum of squares of errors, you know, the summation of this EI square. This line will have the minimum sum of squares. So that has been said the method of least square estimation in linear regression. I think you have learned already this in your basic biostatistics course actually. So suppose with this formula, for example, the outcome variable y could be a systolic blood pressure is equal to the intercept A or alpha is 98.71 without any consideration of predictor variables. Plus, if we do have an additional predictor variable age, and if the beta coefficient, that means the effect of a 1 year increase in age on systolic blood pressure, if it is 0.97. So the formula will be this. Then, if an individual have a 45 years of age, then 45 multiplied by 0.97 plus 98.71, the intercept, the predicted systolic blood pressure will be this much. If an individual have 55 years of age, then multiply this 55 by this beta coefficient and then add this constant or intercept, so that the predicted systolic blood pressure will be 152. If an individual have a 65 years of age, multiply this age by this beta coefficient and add this intercept. Finally, the predicted systolic blood pressure will be 161. You see how the increase in age would increase the systolic blood pressure? That is the way of prediction. That means knowing the change in the outcome variable given the change in the independent variable. You see, the change of the independent variable is 45 to 55, from 55 to 65. So the change in the independent variable changes the outcome variable. That is prediction or regression. Knowing the change in the outcome variable given the change in some amount of the independent variable. That is regression generally. So in the case of multiple linear regression, what will be special or different from simple linear regression is we will have more than one predictor or more than one independent variable, as you know. So the outcome variable y is equal to the intercept beta naught plus beta 1 x1, the beta coefficient for the first predictor variable, beta 2 x2, the beta coefficient for the second predictor variable, plus up to beta k xk. If we do have 10 predictor variables, there will be a list of 10 predictor variables with their own beta coefficients, you know. And finally, always there will be the error term. This is the formula for the total population. And for the sample, this will be replaced by the letter B. And the estimated or the predicted outcome variable will be y hat. The intercept B0 plus beta 1 x1, B2 x2 up to bk xk. Like for example, the birth weight could be an outcome variable. And then the first predictor variable could be maternal age with its beta coefficient. And the second predictor variable will be the sex of the child with its beta coefficient. The third predictor variable will be the gestational age with its beta coefficient. And the fourth will be the parity of the mother with its own beta coefficient. So each of the predictor variables will have their own beta coefficient. That means their own effect on the birth weight of the baby. That is a multiple linear regression idea, you know. Now we are on the verge of just to go with logistic regression. And I need to just cut the video here in order to make the size to be appropriate, you know.